Hello everyone, I thank IAVM for giving an opportunity to share my research work related to applications of Vedic mathematics sutras in digital system. My presentation sequence goes like this. I am going to discuss what are the needs of current digital system, multipliers and adders in digital system, the working of binary adders such as half adder, full adder, ripple carry adder, carry look ahead adder, how Vedic mathematics sutras can be applied to the digital multipliers, and one implementation of 64-bit by 64-bit multiplication using Urdhva-Tiryak method, and finally conclusion. Over the years, as a result of expanding signal and computer processing application, the demand for high-speed processing has seen a constant increase. Arithmetic operations with higher throughput are essential to achieve the required performance in many real-time applications. Fast and low power consuming systems are the need of the current technology. Design and development of low power microcontroller applications and digital signal processors which work at a very high speed is a challenging task. The speed of digital processor is directly dependent on the speed of multiplier. The performance of multiplier depends on the adders used in logic circuits. Vedic mathematics provides one of the fastest multiplier algorithms. Now let us look into different multipliers, digital multipliers and adders. A binary multiplier used in digital electronics is an electronic circuit to multiply two binary numbers. The types of multipliers are Brown multiplier, combinational multiplier, Booth multiplier, modified Booth multiplier, Bob-Wole multiplier, Dada multiplier, Wallace-Tree multiplier. Coming to digital adders. Addition is a fundamental operation for any digital system. The extensive use of adders for basic digital operations such as addition, subtraction, multiplication and division makes it a very important component of digital systems. So, enhancing the performance of an adder influences the performance of other operations, in turn the digital systems. The types of adders are ripple carry adder, carry look ahead adder, carry save adder, carry skip adder, carry select adder, etc. Binary adder. A combinational logic circuit which can be constructed using a few basic logic gates allowing it to add together two or more binary numbers is the binary adder. A basic binary adder circuit can be made from standard AND and XOR gates allowing us to add together two single bit binary numbers A and B. When we add two bits like this A and B, we get two outputs. One is sum and the other one is a carry. Half adder circuit. A half adder is a logical circuit that performs an addition operation of two binary digits. The half adder produces a sum and a carry value which are both binary digits. Now let us look into the left hand side table. So when we add 0 plus 0 is 0, 0 plus 1, 1, 1 plus 0 is 1. When we want to add 1 plus 1, so we get 1 plus 1 is 0 sum and also the carry is equal to 1. We are going to get it here. Now let us look into the truth table. We have A and B are the two inputs and sum and carry are the two another columns are there which are the outputs here. When you carefully observe the carry here and also the A and B inputs, when both A and B are 1, the carry is equal to 1. So this resembles AND gate. So hence the carry can be obtained by ANDing of A and B. Similarly, when you look into the sum, when A is 0 and B is equal to 1, or when A is equal to 1 and B is equal to 0, the sum is equal to 1. In the remaining cases, it is equal to 0. So hence the sum can be obtained by XOR of two inputs. So therefore, when we look at the symbol of the half adder circuit, the sum is the XOR of the inputs A and B, and the carry is the AND of the inputs A and B. But this half adder is not sufficient because it is possible to add only 2 bits. When you are going to add 2 numbers, so it is we are going to get the carry. Hence, to address that carry, so we need to take care of that carry and add it to these bits. Hence, we come across full adder. The full adder is a logical circuit that performs an addition operation of 3 binary digits, and just like the half adder, it also generates a carry out to the next addition column. Then a carry in is a possible carry from a less significant digit, while a carry out represents a carry to more significant digit. When we observe this full adder block diagram, we have 2 inputs A and B, and Cin is the carry obtained from the addition of previous 2 inputs, and we get a sum and a carry. So when you look at to the right hand side box, we have Cin, A and B. So we obtain the addition of these 3, so that we are going to get a sum as well as a carry. So let us look into full adder circuit. So it is a combination of 2 half adder circuits, hence 3 bits can be added together. So therefore the sum is given by A XOR B XOR Cin, and carry is given by A and B plus Cin into A XOR B. So we understood the addition of 2 bits along with a carry here. Now let us see, when you want to add 2 n-bit numbers here, assume for example we want to add 2 numbers A and B, so which are having 4 bits each of them, that is A0, A1, A2, A3, and similarly B is B0, B0, B1, B2, B3 here. So hence for addition of these every 2 bits here, we want to have a full adder. When we want to have 4 bit addition, when we want to have, so hence 4 such full adders are required. So to add together 2 n-bit numbers, n number of 1-bit full adders need to be connected, or we are going to call cascaded together to produce what is known as ripple carry adder here. So we need 4 full adders for 4-bit addition. Observe, A0, B0 are given to the first full adder, A1, B1 to the second, A2, B2 to the third, and also A3, B3 to the fourth full adder. And a carry into the first full adder is 0 because there is no carry from the previous, because A0 and B0 are the LSB of the given 2 4-bit numbers. Once these A0, B0 and this Cin which is 0 is added, we get sum S0 and C out. We get C0, this C0 is given to Cin of the next full adder, which is added with A1, B1, and we get the sum S1, and C out, which is C1 which is given to the next adder, which is added to A2, B2, and so on, so that we get the total output as C out, S3, S2, S1, S0 put together is the addition of 2 4-bit numbers, that is A and B. Now in this case, this is called as ripple carry adder. Unless you get the carry C0, which is the addition of A0, B0, we cannot compute A1, B1 along with C0 to get S1. Similarly, unless C1 is obtained, we cannot do the computation of this. So hence the carry is ripples through so many such full adders. As the number of bits are increased, so the delay is also increased in this case. To avoid this, we can have carry look ahead adder, where we can have still more complex circuit at a cost, but we are going to reduce the delay which is obtained in the addition of these 4 bits, which is available as an IC called 74LS83, where first binary number is represented as A3, A2, A1, A0 you are going to give, and similarly the second binary number B3, B2, B1, B0, and a Cin input, C out, along with that sum output as S3, S2, S1, S0, so that we can add 2 4-bit numbers. Also we can do the subtraction of these 4-bit numbers also. When we want to add 8-bit numbers, you can use 2 such ICs cascaded together, where the Cin for the first IC will be 0, and the C out is connected to the Cin of the next IC, so that we are going to get a 8-bit addition also. So this is the basic discussion related to the how addition is going to take place in case of digital systems here. Now let us look into Vedic mathematics and how we can think of applying this Vedic mathematics to the binary system. So Vedic mathematics sutras are currently known to be easily applicable to decimal number system. So for it to be applicable to digital system, it is necessary to establish the correlation of sutras with a binary system. So although digital systems are working based on binary number system, so the hexadecimal number system is used for ease of representation. So establishing this correlation will give a great insight into implementing Vedic mathematical sutras in digital system. So now let us discuss decimal, binary and hexadecimal number system. Now decimal numbers, we go from 0 to 9 and further 10, 11, 12, 13 up to 50. So we can represent these numbers in terms of binary with 4 bits, that is 0000, 0001 up to 1111. So hexadecimal numbers we can represent 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then this 1010, which is 10 decimal, it is represented as A, then B, C, D, E, F. So F is 1111. In hexadecimal number system, the terminologies are used. So we have nibble, that is 4 bits. Take an example 1010, which is represented as A. I have omitted, that is H is written along with this, which is representation of hexadecimal. So for ease of understanding, I have omitted, that is A. I am going to write it here. A byte is 8 bits. This is 1001, 1110. So this 1001 is 9 and this 1110 is E. A word is 16 bit. So similarly we can easily represent. This color coding is only for the understanding purpose. Now let us discuss how we can apply this Vedic maths to binary system. For the reference purpose, in the right hand side of the presentation we have decimal and also the equivalent hexadecimal numbers are given here. Now let us think of applying Nikhilam Sutra. We know like 6 into 9, when we multiply, I am going to subtract 1 from 6, that is 5, and 9 minus 5 is 4. Similarly, a 2-digit number also. Now coming to the hexadecimal system, so I am multiplying this hexadecimal 4 into F. Now F is going to play the role of 9, how we apply in decimal system. F is the highest number in hexadecimal number system. Now I want to multiply 4 into F. So how we multiply 6 into 9? In the same way we can apply here. We subtract 1 from 4, that is 3, we can see here. Now F is here 15. Now 15 minus 3 is 12. The equivalent is C. So hence the product of 4 and F is 3C. Similarly 7 into F, subtract 1 from 7, that is 6. Then F minus 6 I have to do. So 15 minus 6 I am going to get 9. So 69 hexa is the product of 7 and F. Similarly let us think of applying it to 2-digit numbers, that is 8-bit numbers in case of hexadecimal. 23 hexa into FF hexa. So 23 minus 1 is 22 and F minus 2 I am going to get 22. DD is hex is the answer. Now applying Yavadunam Sutra, 9 squared is 9 minus 1 because it is 1 less than the base, and 1 squared we write 81. Now coming to hexadecimal, F squared. So F is 1 less than the base. Now in our hexadecimal 16 is the base. So F is 15. So it is 1 less than 16. So F minus 1 and 1 squared we get the answer is E1. Similarly D squared. So D is 13. So D 13 is 3 less. So therefore reduce it by 3 and also write the square of that. Therefore we get A9. Similarly we can go on. Applying Ekadikena Purvena, 25 squared as we know. So squares of numbers ending with 5. We multiply 2 into 1 more than that, that is 2 into 3, that is 6, and simply write 5 squared, answer is 6 to 25. Now the role of 5 is taken by 8 in our hexadecimal system, which is half of the base here. So how in the decimal system 5 is half of the base, so 8 is half of the base, that is 16. Now 18 hexa, I want to square it, means we can directly apply how the Ekadikena Purvena, how we are going to apply in the decimal system. So 1 into the next number, that is 2, and 8 squared. So 8 squared is 40 hexadecimal. So whatever the numbers which are represented, all these are hexadecimal in this case. So 1 into 2 is 2, 8 squared is 40 hexa. So 18 hexa square is 240 hexa. Similarly, 28 squared we want to do. 2 into 3, then 8 squared, so 640 hexa. Let us go ahead. Ekadikena and Antyayor Dashake api. So 34 into 36, the unit place sum is equal to 10, and the decimal place numbers are same. So we multiply 3 into 1 more than that, 3 4s are 12, and 4 into 6 is 24. The same is applicable in hexadecimal. 2e into 22 we want to multiply. So at this place, that is the upper nibble what we take. So 2 are same, and the lower nibble is e and 2. So e is 14 and 14 plus 2 is 16. So we can directly apply Antyayor Dashake api. So Dashake api in case of decimal is 10. Dashake api we can apply here also for hexadecimal. If the sum of the lower nibbles is 16, we can apply. So 2e into 22 is 2 into 3 and e into 2, which comes to 61c. We can go on trying like this. Now applying Nikhilam Sutra, I want to multiply 8 and 7. So 8 minus 2, 8 is 2 less than 10, and 7 is 3 less than. So minus 2 into minus 3 is 6. 8 minus 3 or 7 minus 2 or 10 minus 2 minus 3, which is equal to 56. So consider multiplication of e and d. E is 14, it is 2 less than 16, so therefore e minus 2. D is 13, it is 3 less than 16, so multiply minus 2 into minus 3 is 6. E minus 3, we are going to get b6. Similarly, coming to vertically and crosswise, so 23 into 21 we will get 483, and you can apply e2 and 33 multiplication. So 2 into 3 is 6. Now crosswise you multiply e into 3 plus 3 into 2, which is 30, and e into 3. Finally we get 2d06 is the answer here. So we have discussed so many methods we have applied. This is what is called as line diagram for binary multiplication using Urdhva Tiryakbam. This architecture is built by Professor Arun Kumar in electronics department. So we can see two half adders are there. So architecture of 2 by 2 multiplier. So when you want to have 64 bit by 64 Vedic multiplier, it can be arranged in this way. I have taken this slide from Arun Kumar presentation. And let us have a comparison of these multipliers. So currently known best multiplier is applicable is Karastubha multiplication. And coming to the last row in case of delay, so Urdhva Tiryakbam applied to carry skip adders, carry lookup adder, and carry select adder. So we observe that these applications are giving very less delay when you are going to use multiplication here. So some observations can be made. Vedic math sutras are also applicable to hexadecimal number system. The adders used in current system use shift and add method for multiplication. By suitably combining the compare, complement, shift and add methods, it should be possible to design adders that would perform in a better way by utilizing lesser clock cycles for computation. So in turn, better multipliers can be designed which further enhances the performance of digital system, in a way opening new avenues for Vedic digital research, resulting into true green computing.